That is incorrect. Right, good afternoon everyone. We're going to continue now with the aeroelasticity lectures. We're going to look at quite a complicated example of a phenomena that occurs on supersonic missiles, which is panel flutter. And the reason that we're going through this example is because it captures all of the things that we looked at in the preceding modules. So we use sort of a finite element model to build this model, and we use virtual work methods to build up the non-conservative aerodynamic forces. So it's just to show you that we do use these methods to build up real models. So Flutter, we sort of loosely spoke about in the introduction to this course, and I'm now going to go and just talk a little bit about Flutter and what it actually is. So aeroelastic flutter, as distinct from atrial flutter, which is something that occurs here. So we drew up Coller's triangle yesterday, in which we've got these three types of forces: aerodynamic, inertial, and elastic forces. So this is just the fact that we've got a solid body that interacts with a moving airstream, generates circulation, and also viscous effects, which give rise to the forces that we know as lift and drag, but they are generally the aerodynamic forces, also a pitching moment as well. Inertial forces arise because the body, anything that has mass, we said it has an inertial resistance to acceleration. So if the body is made to accelerate, then there is this reaction force that we get from F equals ma, and we spoke about that in terms of a plunging wing. There's this inertial force that is mh double dot. And then elastic forces, this is just the forces due to Hooke's law. Okay, so if we have an elastic system, if we have an extension, then there must be, a force is required to generate that. And this is where we have that KQ equals P setup. The stiffness multiplied by displacement is equal to forces. So most of what we're looking at in this module is largely going to be the look at aerodynamic and elastic forces. And we're looking at the interplay between these two forces. So we're going to look at torsional divergence and control reversal. If we have to involve the mass in a problem, it becomes a lot more complicated. So there are several different types of flutter, and flutter is a problem that contains all three of these forces that can occur on an aircraft. So we're going to talk about those, and then we're going to look at an example of a specific one today. I'm going to put up here, it can be unsteady. Or typically, flutter describes the unsteady vibration. Okay, sort of, it depends whose textbook you read. Flutter might be the unsteady point at which that vibration suddenly becomes catastrophically unsteady, or it might be the motion itself. But we'll say it can be unsteady, and we'll say catastrophically unsteady. So there are several different types. So several different types of flutter. The first we'll call wing or control surface flutter. Or say wing, rather aerodynamic surface. So AS just means aerodynamic surface, so this can occur on horizontal tailplanes or vertical tailplanes, for example. This is often also called classical flutter. And the seminal work on classical flutter was performed by a guy called Theodor Theodorson. Wonderful beautiful mathematics in his solution. We probably don't have time to go into that in this course. In fact, I know we don't have time to go into it. I wish we did, and I might produce some bonus lectures that no one's going to watch at the end of this. But this is a combined bending and torsion vibratory motion. And it involves unsteady aerodynamic feedback, which leads to negative damping. And by negative damping, we mean that the aerodynamic forces give rise to an increase in the oscillation of this vibration, which is why we see this can be catastrophic, because then something starts to vibrate. Normally, for the reasons that we discussed in the last lecture, those aerodynamic forces tend to be damping. They tend to give positive damping, which reduces the energy of the system. If we have negative damping because of unsteady aerodynamic effects, then this can lead to an increase in the vibratory amplitude, which causes wings to snap off. Okay, I'm going to put a link shortly in the video to a great couple of videos. There are thousands of them on YouTube of these sorts of motion. In fact, the Tacoma Narrows Bridge, which I know you will have all watched because it's an example that is given to every freshman engineering or every engineering course. Everybody has seen the Tacoma Narrows Bridge. That's an example of classical flutter, because you see the bridge twisting and bouncing at the same time, and unsteady vortex shedding will be the cause of that vibratory motion, and then it would have been negatively damped. Negatively damped because of the aerodynamic effects. We also have propeller whirl flutter. This is the motion basically on propeller blades or propeller discs. The fact that we've got a propeller that's on a nacelle which can nod up and down around the thrust axis, and then we've got a dirty grey gyroscope on it. I'm not going to give any more details of these, and I'm not going to test you on these, but I want you guys to know about them. We also have stall flutter, which occurs again on propellers. And then we've got this last one, which is a panel flutter. And that's the one that we're going to look at today, okay? So this occurs on supersonic missiles. Okay, so I'm just going to put a link to a video that I want you guys to watch. This gives examples mainly of wing surface flutter, wing or aerodynamic surface flutter. So just observe the short build-up time, the very quick and large vibrations, and in some of these videos, the ones that were taken in wind tunnels, you'll see the aerodynamic surface snapping off. Obviously, this is a catastrophic phenomena. We need to be able to predict when it occurs. We need to be able to predict the speeds and the things that build up to it. And to do so, we need an aerodynamic model. We need not just an aerodynamic model, we need a mathematical model for all of these things. So we're going to I'm going to introduce some Lagrangian mechanics that will help us understand how to do this. Okay, so that's inertial, aerodynamic and elastic forces. The sorts of problems that we face in aeroelasticity involve the exchange of inertial, aerodynamic and elastic forces. So we have flexible aircraft wing, bending all over the place. This is obviously a highly exaggerated example, but we could have a wing that is able to twist. So we have wing torsion. Let's make this a little bit smaller. have wing bending. Have a free stream velocity, which we'll call U, just to put you in good stead for aircraft flight mechanics. And then we've got a changing aerodynamic load on the wing. Let's write the word changing properly. And it changes for the reasons that we've discussed. If we have a wing that is bending about, okay, so let's pretend rather than this being a roll motion, this is because of wing bending. It will cause a plunge velocity. It will cause an effective change to angle of attack. When the wing's undergoing torsion as well, that changes the angle of attack, which changes the forces on the wing. So we need a mathematical model of this sort of problem. And we can do that. We can take a representative section, for example. So we might take a representative section of the wing and make a two-dimensional model. Okay, so we've got the nominal aerofoil section of our wing now. If we know, for example, that our wing has a certain torsional stiffness, we can then model this with a torsional spring at whatever the position of the elastic axis is on our wing. So let's say this is the elastic axis, or the shear center of this two-dimensional section. Then we can represent that torsional stiffness with just a simple spring, and we call the stiffness of this spring has the symbol Kd. Okay, we could represent the mass of the wing at the inertial axis. This we just give the symbol m. This would be the mass per unit span. We also know the wing is able to bend, and again we model that with a linear spring at the same location as the torsional axis. Give this the symbol KH. Okay, remember H for plunge. So we then have this plunge velocity H, sorry, plunge displacement H. Plunge velocity would be H dot. And then we've got these aerodynamic loads that we can look at on the wing. So we would say that wherever our aerodynamic center is for this particular aerofoil, we would have the lift working on this wing. So we've got torsional stiffness, Kd, and we've got plunge or bending stiffness, Kh. So that's our sort of simplified mathematical model that we're going to use, and we will be using this next week when we look at a divergence model and when we do a model for control reversal. This is probably the simplest this model could be. We could complexify it. We might be looking at the effect, for example, of the control surface. So say on our wing we want to know what the effect of the aileron is, and we want to look at the aileron effectiveness, and we can modify this model by just simply including that in our system. Let me erase a bit more in here. Give this the symbol, whatever we want to call, say beta of the aileron, for example, if they were looking at the wing. We then have a second mass in here, and we would then have to have a torsional stiffness here, and we would call this K beta, for example. Okay, so we're going to be making this model more complicated if, for example, we wish to explore the effect of aileron deflection. or control surface if we wish to look at control surface deflection. Okay, so we will actually be using these. I'm going to draw one more example that we often would look at in aeroelasticity, but we probably won't have time to in this course. We often look at rotating systems. I don't know how familiar you guys are with helicopter hubs, but helicopter blades are able to flap, which means they are able to have an out-of-plane hinge. They've got an in-plane hinge called a lead lag, and then they've got a pitch or a feather hinge, which enables you to change the angle of the blade. Those are related to blade dynamics, but they mean that we've got this system that's doing all these complicated things. So if this is my rotor hub, then I've got a rotation. I've got a rotational speed omega, and I've then got a hinge that enables the blade to flap. I've then got a second hinge which enables this in-plane rotation, and I would then have a third hinge which we might just model, for example, like this, and then we get to the blade, which we would give again some sort of mass and some sort of unsteady aerodynamic loads. So that's flap, lead, lag, and then here we have pitch, or maybe feather, depends again whose textbook you're reading. Big difference with this sort of system is that we have rotation, and it becomes horrendously difficult to keep track of the forces because of Coriolis effects, because of centrifugal effects, and all of the axes transformations that we would have to do. But the reason I'm drawing these and the reason I'm bringing them up is that because these systems up here, these two that we're actually going to be using, and these sorts of systems, it's very, very difficult to keep track of the number of forces in this sort of system. It's not impossible, but it's very, very difficult. So to model these systems, the number of the forces and the displacements in the entire system just gives rise to too many vector quantities. What do I mean by too many vector quantities to keep track of? Well, we know that if we're looking at a three-dimensional system, for every force and for every displacement, we need to know its three components. If we are then having to look and we're then summating forces in any given direction, it's a tremendous amount of trigonometry to do. So the problem becomes very large and unwieldy. So to solve these sorts of problems, then we consider one of the greatest principles in physics, and we've dealt with it before. It's the interplay of work and energy, because both of those are scalars. And we found this useful back in module 2 because this enabled us to solve for displacements using virtual forces, things that we just invented to try and look at the relationship between the total energy within a system and the displacement at a point. And we're going to find this really useful within aeroelasticity. So for example, if we were to look at a very simplified model of our wing system, where we just, for this first part, we're just going to look at torsion. I'm going to say we've got a centre of mass aligned, sorry, not torsion, bending displacement rather. If we have a centre of mass aligned with our inertial axis, then we'd have a spring here, kh. This would be again our bending stiffness. Let's put the lift on here. Then we've got these three different types of forces. We've got inertial, aerodynamic, and elastic forces that we can then put into work energy formulation, or we can find energies associated with these. So kh, we need to look for an elastic energy, and for us that's going to be strain energy. H squared, but remember h is the plunge displacement. Okay, so we've got strain energy occurring. We've also then got inertial forces. If we have a mass and it's moved through a velocity, we have kinetic energy, so half mv squared. And since the velocity in this plunge direction is going to be equal to the first time derivative of h, that just gives us a half m h dot squared. And then with lift, if we've moved through a displacement, lift is acting upwards, plunge is acting down, so the work done by the lift is equal to minus L multiplied by h. So by just setting this problem up as a problem like this, we can see that all of these have to be equal, and in this complicated problem, all that's happening is energy is being converted between these three forms. So what that means is if that's these quantities must sum to the same amount, which is the total energy within the system, then accordingly the equations of motion of the system are hiding somewhere in that description of the system energies. And it's when I write these sorts of phrases down like this, the equations of motion of the system are hiding somewhere within the description of the system energies. That's a phrase that I would have written down in my penultimate year of my aerospace engineering course. Almost word for word, this is taken from what I was taught as an undergraduate and was fascinated by this concept. Okay, so a good thanks to Dr. Gillis, who I'll probably screenshot this little bit and send it to him, and who you can maybe feel proud. So we are going to look at the interplay of potential energy and kinetic energy. Okay, so we're going to look at potential energy is generally stored in this strain energy, and then kinetic energy up here. We're going to look at the interplay between those two. So we're going to rely upon a set of equations and techniques developed by Lagrange. Now Lagrange, very, very famous and talented mathematician, developed a general formulation for the equations of motion of any system. Okay, and we're going to use that exact formulation, and then we're going to go through this example for a panel flutter model, and we'll find that we can relatively easily develop the equations of motion. And that's amazing. You found this way, the general form of the equations of motion of any system. Okay, so this will become clearer, but I'm going to read out what I've written because my handwriting is sloppy. So Lagrange found a general form for the equations of motion of any system. And if we've got a system with n degrees of freedom, so that would be equal to, for our truss problem, that would be equal to 2 times the number of nodes. Okay, so n would be equal to 2 times whatever the number of nodes. Lagrange's equation can then be used, and I'm going to give that to you in a moment, to yield an equation of motion relating the energies at that generalized coordinate. Okay, so that would then give us, if we have a system with n degrees of freedom, we end up with n equations of motion for the system. So Lagrange's equation is d on dt, so the first time derivative of the partial derivative of the kinetic energy with respect to the first time derivative of that generalized coordinate. And this will all make more sense as we go through. But this equation, we're just going to use it today to see how we get things, how we can actually use it to build up these equations of motion. Minus the partial derivative of the kinetic energy with respect to that coordinate, plus the partial derivative of the kinetic energy with respect to that coordinate. And that's going to be equal to these non-conservative aerodynamic forces on the right-hand side. Now I'm going to use pi for the right-hand side of this, just because that keeps this convention in keeping with the rest of the work that we've done. Okay, if you look at the Hodges book that I've linked to and where this example really comes from, then they use an uppercase QI there, but I know that's just going to confuse you guys with the generalized coordinates earlier. So on this right hand side we've got these non-conservative aerodynamic forces, or the work done rather by non-conservative aerodynamic forces. Okay, so if we have I is equal to the number of degrees of freedom, then we have this many sets of equations for that. Okay. Oh, and I didn't even write this down on here. So T is going to be equal to the kinetic energy, and V is going to be equal to the potential energy. And potential energy for our problems is almost always just equal to the strain energy. Okay, so we've got these two things, kinetic energy, potential energy, and then on the right hand side we put these formulations in for the aerodynamic forces in a format where we can come up with the work associated with them. So if we want to look at the system and how we're actually going to see that we can build up this interplay between kinetic, elastic and aerodynamic forces, the aerodynamic forces go in here, the inertial forces are involved in the kinetic energy because we've got a mass that's being accelerated, and because we've got a mass that's being accelerated, and then we've got potential energy. This is where we have that strain energy, or those elastic forces coming in. So the Lagrangian, so I called it Lagrange's equation up here. Sometimes you'll be heard it called the Lagrangian. Okay, so the Lagrangian is used to develop equations of motion for all manner of aeroelastic problems, and we're going to use it to develop a simplified flutter model. So we're going to use it to develop a model for panel flutter. Okay, so let's talk about how we're going to do that. Okay, so panel flutter is a vibratory instability that occurs on supersonic missiles, or it would occur on any supersonic thin-walled structure. Okay, so we're going to talk about that and develop a model for it today. Okay, so it was first observed on the V2 rocket, so dirty great bomb with a rocket on the back of it basically, but this was an impressive flight vehicle. Maximum speed of 3,750, no, 3,570, I think actually, I got that wrong. Still very fast, and it could go up to Mach 1, break the speed of sound in 25 seconds. But like any rocket that would have this rib and panel construction, so we've spoken a little bit about that. Well, we've spoken about that quite heavily actually. So these rockets would be, in general, would look like a tubular structure comprising ribs, and then we'd have flashy different colored panels to make things obvious, and normally some fins at the bottom as well for stability. Okay, and so it can stand up on its own. Now if we were to look at the actual construction of how these work, then we'd see ribs here and thin panels. Then if we were to zoom in on what actually occurs there, we'd have these very rigid ribs connected by a very thin panel. Panel has 1L. I don't know why I tried to give it 2. Now, going past this panel, speeds much higher than the speed of sound. Okay, so very large flight speeds occurring versus here. We know that these thin panels, much like the skin of an aircraft wing, isn't good at taking load in this direction, so it's able to vibrate in this direction, and after a certain speed, a vibration builds up. Let's copy this diagram. we see a vibration build up that would be low in amplitude but high in frequency. So this motion occurring, this out of plane oscillation of the panel. Now, I don't know too much about the specifics of panel flutter on the V2, but we know that even if it's low amplitude, anything high frequency and high frequency deformation isn't good for any sort of mechanical system because of fatigue issues. Much like bending a paperclip too many times, it will snap off. Or, for example, the comet windows. Okay, repeat stressing at different frequencies is very, very bad for any sort of structure. So we're going to build a simplified model of this, and we're going to develop the equations of motion of it. And then I'm going to give you guys a separate, I might record a lecture on it, I might not. I'm going to give you guys the solution of it. I'm not expecting you guys to be able to repeat the solution, but I'd like you guys to look at how we actually solve these problems. But I would like you guys to be able to understand and repeat how we build up this sort of mathematical model. So we're going to model a single panel between rigid ribs, and we're going to model it as 3 rigid plates. Okay, so rather than being a continuous structure that can bow out, we're going to, so if I've got my, let me continue what I'm writing it and then I'm going to draw it. So we're going to model a single panel between rigid ribs, a single flexible panel as 3 rigid ones. So let's say that I've got 2 ribs here. In real life, my panel is flexing out like that. Then our model, we're going to split this up into 3. So let's and we're going to model this as 1 rigid panel, 2nd rigid panel, and a 3rd rigid panel. So these are unable to actually have an out of plane deformation themselves, but they are able to deform as one. Sorry, not able to deform as one, but able to rotate, and we have associated stiffnesses that we're going to include here and here. Let's check I'm doing this diagram properly. I'm checking the same convention as I've done before. Yes, okay, so we're going to say that these 2 springs have the same stiffness, which we'll just call K. And we've got some dimensions that we can put on here. We say, let's call each of these panels has the same length L. And again, this example, fully included in the textbook that I gave you guys look at. It's Dowell's A Modern Course in Aeroelasticity. I think that's the right author name. Let me double check. It's called, the book is A Modern Course in Aeroelasticity, and I think it's by, yeah, Dowell of Dowell and Hodges, but the author is Dowell, D-O-W-E-L-L. Okay, so this is our system. We need to include some masses for each of these. So let's say each of these has an associated mass, which we're going to call M on each of these. Each of these panels has the same mass for our model. and we're going to include a displacement direction here. Let's say this is our underformed location. So we're going to say this displacement, we give the symbol W, and then we're going to say this direction is our X direction for this model. And again, we've got one rib here and a second rib here. So this red one is going to be our model, the blue one's just included to show what we're trying to model in this situation. So remember the Lagrangian, let's go back to it. We need the kinetic energy and the potential energy of the entire system, and then we need to do derivatives with respect to some sort of displacement or a generalized coordinates. So those two generalized coordinates are just the displacement here and the displacement here. So let's write those on. This one is Q1 and this one is Q2. So we have two generalized coordinates here, Q1 and Q2. So Q1 and Q2 are simply the displacement of these two nodes, okay, the junctions between these two boundaries, and that means we're going to have two equations developed for this system. So let's start off with firstly going to get the kinetic energy. Okay, so the general expression for kinetic energy is a half mv squared, but we've got a mass that's distributed, so we've got 3 point masses on here, and the velocity is going to vary as a function of this x direction. Okay, so velocity really we're looking for if this q is increasing in some time, let's say from time 0 to time 1, q increases from 0 to some value, then we've got an applied velocity upwards of this plate. So we then need to come up with an expression for the kinetic energy contained within that plate. There we go. I shouldn't have necessarily drawn these as point masses here. Sorry, that's incorrect. These should be distributed masses. We'll say that each of these plates has a mass per unit length. Okay, that was my mistake earlier. These aren't point masses. These are descriptions of the mass per unit length. And each of these plates is identical, so that we just call that m on here. Okay, and the velocity varies across the plate length or with x, so we have an integral expression for the kinetic energy. Okay, so we're going to call it t because that's the formulation we use in the Lagrangian. So t is going to be equal to the integral up to 3L to 0, M, and then whatever the velocity is going to be. So it's going to be the rate of change of that displacement, which we've called W, because W is not the same as Q1 and Q2. W is just this, wherever we happen to be on these plates, that is the vertical displacement. It's going to be the first time derivative of that. So it's going to be dW on dt squared dx. So we need to do this expression, and once we've got this, we then have our kinetic energy of this system. We're going to split it down into 3 plates and do it separately because that's easiest. So our first plate, the displacement at the rib is 0, displacement at the length L, or x is equal to L, is going to be Q1. And then we have this distributed mass m per unit length. And let's just remind ourselves that x is this displacement here. So what we need is an expression for w as a function of x. Just from similar triangles, we should be able to see that w over x is going to be equal to Q1 over L. Okay, that's just from basic geometry on there, which gives us immediately an expression for W. So the vertical displacement of plate 1 is equal to, it's a function of x, so x multiplied by Q1 on L. So we can see that solves that when x is 0, it's equal to 0, and when x is equal to L, this is equal to Q1. So we know this makes sense. We ultimately want the time derivative of this, so we take the time derivative. The only thing that's going to be changing is the generalized coordinate Q1 here, because x is just a constant, so is L in this. Well, x is actually just a variable, L is a constant. So Q1 dot on L. So we have that. That enables us to put it into our expression up here, and this then gives us the kinetic energy associated with this first plate. Okay, so the limits of integration is from 0 to L, and then we're going to put this expression, and we need to square it. So we can see that's just going to be x squared, Q1 dot squared, and then L squared in there. So if we perform the integration, x cubed on 3, Q1 dot squared on L squared, and then the limits are L and 0. So this becomes L cubed divided by L. So we end up with the expression 1 on 6 m Q1 dot squared multiplied by L. So this is the kinetic energy contained within this first plate as a function of the first time derivative of that generalized coordinate. Now we need to do the same for plate 2. Plate 2, we'll draw that there. Let's draw this undisturbed condition. Plate 2 starts at Q1 and then ends at Q2, which don't necessarily have to be the same. So then the displacement is going to be, let's just draw down here. So this is my nominal undisturbed line. This is W is equal to 0. We're then looking for this displacement W here as a function of x prime, where x prime is this ordinate starting at this position, the boundary between plate 1 and plate 2. So this displacement here is Q2 minus Q1. So again, from similar triangles, we can see that W, or this is just then a linear variation. It's going to start out at Q1, it's then going to be equal to this distance, multiplied by x prime on L. Okay, using similar logic as we did before. Because again, this whole width here is just equal to L. And then the first time derivative of this, dW on dt, or W dot, is going to be Q1 dot plus Q2 dot minus Q1 dot multiplied by x prime on L. So for the kinetic energy in the plate, this is now our dW by dt. We need to square this to develop an expression for the kinetic energy. I'm going to jump ahead to the end result here, but I want you guys to go through and do the intermediate steps. Drop me a message on Slack. And I've got a bit in my old notes that says, keep track of your squares and your dots in this, because even the instructor doesn't keep track of them properly during the lecture. Okay, so the end result is always fine, but I would advise doing the squaring of this element first to put it into the expression. T2 is equal to half integral from L to 0 m dW on dt squared dx prime. Okay, so square this bit first and you can see what you get. What we'll end up with is okay. Let me just confirm I get the same answer here. Let me just see what I've got. Yes, that's fine. I've just written it in a slightly different format, which is confusing. Let's say 1 on 6 ml. I'll keep this in the same format I wrote the last one. Q1 dot squared plus Q dot 2 squared plus Q1 Q2 dots multiplied together. So do this step, go through it, check you get the right answer, drop me a message on Slack when you've managed to do that. Plate 3, we could do plate 3 by hand, but we can see from symmetry it's just going to be the same as plate 1, but with Q2 in place of Q1. So then we end up with T3 is equal to half ml Q2 dots. Let's check we've got everything here. That should be squared. I didn't have it squared in my crib notes, but it has to be squared. Okay, so we add all these things together for the total kinetic energy. And if we add these up, we see we're going to have a 1 on 6 ml 2Q1 dots squared plus 2 Q2 dots squared plus Q1, Q2, both dotted. So this is now the expression for our total kinetic energy. We can see that it's a function of Q1 and Q2 dot. Okay, so this gives us something that we can see this already. We can put it into matrix form for this expression just as a function of Q1 and Q2 dot. By that I mean that we could have this as the function of some matrix multiplied by the vector Q1 and Q2 dot. And I've called this matrix M here because this describes the mass matrix, which describes the inertial properties of this system. Just as a quick aside, what's really useful about this formulation is if we then went back to this problem and we said, okay, well, we've got these distributive masses here, but actually we're going to redesign the problem. We're going to see if we can damp this vibratory problem, or we need to add a sensor and we need to add a mass, maybe just here, for example. We don't need to redo the whole problem again. We can just add this and we can add it on as a separate kinetic energy to be added to the system. So say that with our problem, we have said we've got these three panels and we want to try adding some new mass here, which I'm going to call M hat, just some added mass. And I've added this on at this location, X hat. We don't need to redo this whole analysis. What we have here is just T from before. The change to T, when we add this, let's call this T prime, is equal to T plus T hat. So this is now the new T with this mass added. And we can see this would just be equal to this value we had before, which is these bits up here, plus on half M hat multiplied by Q1 dot multiplied by X hat on L squared. So we can easily add things back into this formulation, and then this would just be added to our equations of motion. We wouldn't have to redo the whole analysis, and that's really important for this. Well, it's one of the reasons why this method is so very powerful. Okay, so to get the equations of motion from Lagrange, we've now got this T. So we've got T, we need the first derivative of T with respect to Q dot, and then we take the first time derivative of that, and then we need the first derivative of T with respect to Q as well. So let's do those. Okay, so we need both of these things in there. So we need to do this separately for Q1 dot and Q2 dot. So let's do those. dt on dQ1 dot. What we can see up here, well, we're going to end up with a term from this and a term from this. Okay, I'm going to leave you guys to be able to do the calculus in your own time, but we get 1 on 6 ml for Q1 dots plus Q2 dots, and the same dt on dQ2 dots is equal to 1 on 6 ml Q1 dots plus 4 Q2 dots. To get the first time derivative of both of those, we then need to just differentiate these once with respect to time. So d on dt of dt by dqi dots simply equal to this, but with double dots in place of the dots because the mass and the length don't change with respect to time. Call this an I there, that should be a 1. Okay, I just spoke a little bit too soon up here actually when I called this the mass matrix. This wouldn't be the mass matrix. This would be just, I could have some matrix in here. Okay, the mass matrix is actually going to be when we have double dots in here. Okay, because that then gives us a mass and an acceleration, which gives us inertial forces. But I'm just saying that we could set this up in a formulation where we'd have some sort of matrix notation, some matrix, and then Q1 and Q2 dots in this formulation. We could do the same thing down here, and that would then give us the mass matrix. Okay, we've got this bit here. We also need dt by dqi, so that's Q1 and Q2. We can actually see that this expression doesn't have Q1 and Q2 in it. It's only got Q1 and Q2 dots, so these are equal to 0. dt on dq1 is equal to dt on dq2, and that's equal to 0 for this problem. So we've done everything we need to do with the kinetic energy of the system now. We now need the potential energy. And as I said before, for most aeroelastic problems, unless it's really, really significant because we've got very large oscillations, then we don't really look at the interchange of gravitational potential energy. We're going to look at the elastic potential energy for our system, so the energy stored in springs. So V is equal to a half spring stiffness multiplied by spring stiffness squared, or the spring displacement squared. So for our problem here, that's just equal to the sum of k multiplied by q1 squared plus k multiplied by q2 squared, all multiplied by a half. Could have also taken the k outside of the brackets there, but there we go. We also now need, we don't just actually want v, we want dv by dq1 and q2. Just going back to the Lagrangian, we need dv by dq here. So we need to evaluate the terms required for the Lagrangian. So dv by dq1, well, we're going to have this 2 is going to cancel with the half. So we're just going to have kq1 and dv by dq2 is equal to k q2. So we can put all of this together in matrix form. Go back to the Lagrangian here. We can now take, we've got these terms, we've got them, and we've got these terms as well. We know that all of these are equal to 0. We haven't got the right hand side yet, but we can add all of the left hand side terms up and put it into matrix form. So these first terms come from the kinetic energy and the derivative with respect to the Q1 dot, and then the first time derivative of that. These are the terms that come from the kinetic energy. We're then going to have some terms that are related to the potential energy. So we've got stiffness, K, because you've got constant stiffness in this problem. 1, 1, 0, 1. That's going to be equal to something on the right hand side, which we're going to say P1 and P2. Okay, so this isn't a force, this is the work done by aerodynamic non-conservative forces. So this bit here is our mass matrix, because it's something that we multiply with this acceleration here. This one here is our stiffness matrix. So we've set up this left-hand side of this problem. We've done everything in a work energy formulation. So the units are going to be different to what they would have been from previous problems. We've got a stiffness here, but this here is we're looking at the work that's been done by this, well, sorry, not the work, the energy that's stored in this spring energy. We've got the kinetic energy that's in this one here, and then on this right-hand side, we're going to have the work done by aerodynamic non-conservative forces. So we still just need to work out these two things here. And for this, we're going to use a virtual work formulation. So we need these expressions for P1 and P2, which is what I've called them above, as energies. Okay, so we're going to imagine now that displacements Q1 and Q2 are moved by a small arbitrary infinitesimal amount, and we know what that is. That's a virtual displacement. So let's draw the whole structure again. Let's say it's our nominal 0. We've got plate 1, plate 2, plate 3 here. Okay, so this has already got displacements Q1, Q2. Let's use a nicer, darker color of green, if I can get one. Let's draw something blue. We're then going to say that both of these move up by an arbitrary infinitesimal amount. And so we then have we'll say this is delta Q1 star, delta Q2 star. Because we've got this moving airstream, we've got a supersonic airstream here, there's going to be an associated pressure change on these plates. Sorry, there will be a pressure change on these plates due to Q1 and Q2, not because of these on here. I should have written this the other way around. So let me write those on here in purple. We got on here, this would be delta P1, delta P2, delta P3. These are pressure on plate surface due to Q1 and Q2. So if we have a plate and a supersonic surface, then we're going to have a pressure change on it. Now we could show in supersonic flow, and we're not going to develop this in this course, but you should see expressions like this being sort of familiar from compressible flow. It can be shown and supersonic flow, the pressure change on an aerofoil, or pressure change on a plate like this, delta P will be equal to minus rho u squared divided by the free stream Mach number multiplied by dW on dx. So we need an energy associated with that, so we need the delta P multiplied by the variation of W because of these small arbitrary infinitesimal amounts. So our virtual work that's done is going to be equal to the integral. Again, it's an integrated expression of that pressure change multiplied by whatever the virtual displacement dW is dx. And this is going to be the right hand side of that equation. dW is just going to be a function of, dW star is just going to be a function of that dQ1 star and dQ2 star. So this is that small variation that we need, which is delta W star, so that's the virtual displacement at that point, and we can again, from very similar reasoning that we saw before using similar triangles, we can see that delta W1 star, I should put a 1 up there really as well, delta W1 star is equal to delta Q1 star divided by L on X. So that's the virtual displacement due to delta Q1 as a function of the distance X. So then we can evaluate this expression for the first plate. So delta W1, I'm making a distinction here, just be careful, these delta W's are lowercase, this one here is uppercase, meaning total work. So delta W, meaning the total virtual work on this first plate, is going to be equal to the integral from 0 to L of minus rho u squared divided by the Mach number multiplied by d W on dx multiplied by d W1 star dx in this case. Yeah, that's fine because the pressure change has already got this dW on dx. So this bit here is the delta P, and this bit here is this bit we've just determined up here. So we can put that expression in and we can then evaluate the integral. Okay, so we're going to end up with an L squared on 2 here. This whole expression simplifies to minus rho u squared on 2m q1 delta q1 squared. Sorry, delta q1 star. So what we've got here, this is the virtual work because of displacement, because of virtual displacement q1 on that first plate. So this pressure change is caused by the real displacement q1 when moved through this arbitrary displacement q1 star. We can show very similarly. I'm going to sort of skip through these because I'm not expecting you guys to repeat the right hand side of the formulation of this problem. We can show very similarly expressions for delta W2 star and delta W3 star. If anyone wants to go through and do the derivation of this, I'll be very impressed and I will consider it for some extra credit. Go through and show me where these come from. That's what I had to do in my undergraduate course, but things were always difficult, more difficult years ago, as I'm sure your instructors tell you. Okay, so that's the virtual work on plate 2. Should make this clear. On plate 1. And delta W3. It's going to have a different sign because the plate's got the opposite sign deflection, because this plate is sloping down. So we add all of these things together and a lot of terms will actually end up cancelling. So we end up with total virtual work is equal to total W1 star plus W2 star plus W3 star, and when we add all of these together we end up with minus rho u squared on 2m q2 delta q1 star plus rho u squared on 2, and again that should have an infinity because that's the Mach number, 3 Mach number, q1 delta q2 squared. So what we've now got here is the right hand side of our expression here. So we can then put that in this format on the right hand side. This is p1 delta q1 p2 delta q2. In fact, let's not write that down because that's not quite correct, okay? But this is the right hand side of our expression, which we can then put onto the right hand side in matrix formats. So let's take the equation that we had already, which is up at this point. I'm going to copy it. And take it all the way down. And we can now put this right hand side of the equation in. So we've got this common rho u squared on 2 times the Mach number. And then we've got q2 multiplied by q1 squared, q1 star, sorry, and then q1 multiplied by q2 star. And because that displacement can be arbitrary, We just set it to be small, and we end up with Q1, Q2 here. Okay, so this is the total equation that describes the dynamics of this system. Now, in terms of what I expect you guys to be able to sort of do, I would expect you guys to be able to get up to this point, the left-hand side. The right-hand side is a little bit more complicated. If we had time to go through this in a longer course, then I'd expect you guys to be able to go through this, but I wanted you to see the development of the right-hand side, at least in this course. I'm going to produce I don't know whether I'm going to do a video or maybe just a Jupyter notebook on the solution of this, because what this enables us to do, now we've got this system of equations, we've got our mass matrix, stiffness matrix, and we've got these forces on the right-hand side. If we set the right-hand side equal to 0, this gives us the free vibration characteristics of this problem, and we can look for the natural frequencies of this structure. If we look at the right-hand side, we can then find out the speeds at which flutter is likely to occur, panel flutter. So I'm going to produce a little Jupyter notebook that just goes through that. I'm not expecting you guys to be able to reproduce that work, but it's worth you guys looking at as an aside, which means I'm sure 75% of the class won't look at it, but it's there for you guys anyway. Okay, so don't forget, I don't expect you to be able to reproduce the right hand side of this, but the left hand side I'd expect you guys to be able to do. Okay, hope you guys are having a wonderful week. I hope you guys are finding aeroelasticity as super exciting as I do, and I look forward to moving on to more stuff next week. Take care, guys. Just a quick bit here, guys, just coming back. This bit that I started to write down and then corrected myself, it actually was correct. So this bit that we've just developed here is then effectively equal to our P1 multiplied by delta Q1 star and P2 multiplied by delta Q2 star. So this is P1, let me just check. Yes, delta Q1 star plus P2 multiplied by delta Q2 star. So this is the P1, remember the work done by the conservative non-conservative aerodynamic forces. So here, this is showing me what my P1 and my P2 are. So this is P1, and this here is P2. Okay, so that's why we can then put P1 and P2 into this matrix format like this. So remember, P1 is equal to minus rho u squared on 2m infinity multiplied by Q1. So that's where we get this from here. Okay, so I just started to write that down, and then I, for some reason, was doubting it in my head, and went back and just checked, and actually, no, that is fine. Okay, I was erroneously doubting myself. So believe in yourself, guys. Take care.